high school. I guess as my poster or as my presentation loads, we can talk about what my project actually is. So currently my vision is to allow artificial superintelligence to become a practical reality. And the main limiting factor stopping us from reaching there, outside of sheerly scaling neural network model size and things like that, is hardware. So what is the fundamental hardware limitations that allow or that inhibit neural networks from scaling to becoming state-of-the-art, surpassing the human brain, and things like that? So my project mainly revolves around proposing a novel piece of hardware to run deep learning models past the state-of-the-art, past NVIDIA GPUs and past Google TPU and so on. So I guess my presentation doesn't seem to be loading here.
You can describe it later on the poster, but
Yeah,
you probably need supercomputing.
Yeah. So rather than using a full-on supercomputer or large data centers for neural network processing, what we did was we developed a photonic chip. This is a computer processor that instead of using conventional electricity, conventional electrons to represent and route data, we use photons, which are particles of light that allow for incredibly fast and energy efficient processing. So we created a processor that's mainly tuned towards machine learning arithmetic. The form factor, it's about 0.5 millimeter by 0.5 millimeter. You can't even see it with your naked eye, that's how small it is. But we have actually a few images through a microscope. If you guys want to see it, it's on that poster board over there. That's mainly the poster board that goes into the project. So a bit more about deep learning accelerators in general. I don't know if you guys are familiar with the GPU and the TPU. Those are, if we back up to the CPU, Intel, NVIDIA, sometimes AMD, they create processors that are used in the general public. Like in your own laptop, you have a CPU, and they tune these processors on occasion to run and support larger and larger AI models. This is because as artificial intelligence is growing in demand, we need the hardware that's able to support it. And the downside with this is CPUs are sequential in their processing. They're only able to process one element of data or one instruction at a time, aside from multi-threading and multi-core CPUs, like in general. So to account for this limitation, NVIDIA, a few years ago, a few decades ago, they came up with the GPU. And the GPU, sorry?
1 minute, sorry, we have one more.
Oh, okay. So the GPU is an external piece of hardware that's able to run these models quickly. We propose a new piece of hardware called the MPU, Matrix Processing Unit. It's able to process entire matrices in a single clock cycle using photonic technologies. So if we look at the metrics, I don't think I have time to explain the functionality, but the sheer flops rating, it's at 7 teraflops rating. Per energy efficiency is 245 teraflops per watt. It's at a 220 gigahertz clock speed and has 45 bytes of on-chip memory. And we're working on integrating this processor into your own computer. We want you to plug it in via USB and accelerate all your machine learning intensive applications through this. We also developed a compiler, virtual machine, and so on for you to run deep learning models onto this hardware. And we're working on just creating a full software stack like TensorFlow, PyTorch, where you can select your own custom hardware accelerator that would be our photonic hardware, and you're able to run neural networks ultra efficiently. So in doing this, if I could go into one more thing, is one major challenge that people have when they try to implement deep learning frameworks is tensor sparsity. So what model sparsity is in machine learning is when you create neural networks that have a lot of zeros, they have a lot of null values that come from real world things like missing labels and so on. And the main challenge for deep learning frameworks like TensorFlow and PyTorch is that they have to store these sparse tensors or zero-filled tensors really efficiently in ways that's able to fully leverage even super powerful hardware. So there are major formats that people use to store these tensors. Two of the leading formats are called coordinate format and compressed sparse fiber format. These are able to store even sparse tensors very efficiently. So one thing that we propose in our own software stack to run our deep learning models is a new form of tensor storage that compresses sparse tensors into binary trees and is able to store memory or store tensors in an incredibly efficient way that's on par with the state-of-the-art approaches like compressed sparse fiber, but also has a new feature that allows tensors to be unrolled in constant time in O of 1 as opposed to logarithmic. And it allows such larger, hyperdimensional tensors to be run on our own hardware in constant time. So that's a significant improvement over traditional.
Thanks. Sorry for keeping you on this. It's supposed to not going to be outside. We can have more discussion. One last student, if you want to present.
No, we have Arjun here.
Again, there are two other students, and Arjun.
But one, this is from